No, that's good. Yes, exactly, yes. Okay. Thank you very much, and thanks a lot for organizing this wonderful school. Beautiful weather, good food, everything great so far. So this is methods from geometric group theory. And it's the first of two mini courses on this subject. So Stefan Nami will talk next week to you about different methods from geometric group theory. So geometric group theory is so like in contrast to Cremona groups, like a very young subject. It was more like in the 80s, maybe, or 70s, depending where this was kind of like started to become a thing. And in geometric group theory, people try to study properties of groups by considering isometric actions of the groups on some nice geometric spaces or metric spaces. And I would say like one of the main features in the last 30 years of the field was kind of like it's especially interesting if you have groups that act on certain spaces of negative curvature or non-positive curvature. And it has been like, there are like many different notions and generalizations of negative curvature or non-positive curvature to various metric or combinatorial contexts. And for Cremona groups, that's turned out to be very useful. So one of the strongest tools in this direction is that if S is a surface, then the group of birational transformations of S acts by isometries on some infinite dimensional hyperboloid. So here it's really kind of like a hyperbolic space of infinite dimensional, so it's like through hyperbolic negative curvature. And this has led to various this action has led to very interesting results. Most importantly, Serge Contage showed that the BRS satisfies the TITS alternative. And then another very famous result in this direction was that the Cremona group in two variables is not simple. By Conta and Lamy. Also using this action and kind of like also developing methods called small cancellation. And yes, so okay, this is probably like the strongest tool. However, it only works for dimension 2, so we need that S as a surface. And I will not talk about this one. So this is most probably Stefan Lamy will talk about this next week, and you might also encounter it in the courses on dynamics. It's also like very closely linked to degree and dynamical degrees. This action. Okay, this will be done in other courses. So what we will consider in this course is it will be we will consider actions of BRS on cat0 cube complexes. So Evgeny always tells me I should not use this word because it sounds very technical and scares people from coming to the talk. But okay, it's if people doing metric geometry, they know this concept very well. Although we will use it in a different, in a slightly different variation. So it stands for Carton, Alexandrov, and Topogonov. So it's like 3 initials, and it's like another. So cat0 cube complex is another kind of like generalization of non-positive curvature to kind of like some combinatorial metric setting. And so, okay, what we will do is basically we will look at various actions of BRS. Wait, let's say BRX, because some of the cube complexes will work for any variety. So if X is a surface, we will consider the so-called blow-up complex. That's the one we will construct today, and then on Wednesday we will see that if X is an arbitrary variety, then we get some other complexes. CLX. Okay, so as I said, like these tools are like weaker than this action, but the advantage is, first of all, it's quite elementary, so we'll need a very little algebraic geometry, which is often like people in geometric group theory like this a lot, so they can understand better Cremona groups without having to know what Picard groups are and so on. But also, it works for some part of it works in arbitrary dimension, so that's also nice. And also because it's so kind of like quite elementary, the whole thing is that implies that actually it works over any field. So for us, we will consider varieties over an arbitrary base field. You can also consider K to be algebraically closed. You don't lose anything. Often when you have results that work over arbitrary fields, either it's very difficult and very complicated because you need to consider positive characteristic and so on, or it's actually so elementary that it works over all fields. So we are in this second case. Okay, so the program of today is to, well, first we will define cat-zero cube complexes, see what they are. And then in the next step, we will have a look at the blow-up complex. So let's start with cat-zero cube complexes. So, okay, a cube complex is just, we take just a polyhedral complex consisting of cubes. So we take Euclidean unit cubes of arbitrary dimensions. We take a union of those and we glue them together along isometries between some of their faces. So just a union of finite dimensional Euclidean unit cubes glued together along isometries between faces. And we want that, so okay, no cube can be glued to itself. And also, yeah, we want that the intersection of, so two cubes intersect are either disjoint or they intersect in a face. No. Let's just, okay, it's nothing. Just make some examples, right? Like we can take really like a cube. For example, a 3 cube, okay. Higher dimensional cubes are hard to draw. So this one is filled 3-dimensional cube. Then it has here 2 faces and then 1 faces and the 0 faces. And then, for example, we can attach here a square. Let's attach here a square. Attach here an edge. So various things. Or also, like, we can have 3 squares glued together like that. But inside here it's hollow. Or of course also all graphs are cube complexes. They're just one-dimensional cubes. One-dimensional cube complexes. Okay. Yes, so what is not allowed is, okay. Like you cannot have that they intersect in 2 faces. So such a thing is not allowed. And something like that is also not allowed. Yeah. Good. Okay. And now we can just make the definition. So we say a cube complex is cat 0 if it is simply connected and if all its links are flag. Okay, so hopefully simply connected. I guess everybody is familiar with maybe links and flag we need to define. No, that's not finite, not bounded dimension, everything. Yeah, like the cube complex we will consider are very, very large. They will be not finite of cubes of arbitrary dimension. Uncountably many of nothing. It's not the kind of cube complex that I draw that we will call. Okay, so if we have, let's explain what this is. So if L is a cube complex, and we have a vertex, so a 0 cube in there, then we define the link. So let's say link V, the link of V. So this is a simplicial complex. It's the following simplicial complex, so that so the vertices of the simplicial complex are just the vertices in L that are adjacent to V. And we say that they they form a simplex if they are contained in a common cube. So, so vertices V1 to Vn in the link of V span a n-1 simplex, if well, the set of V1 to Vn are contained in a n cube. So let's look maybe here at some examples. Well, here different vertices maybe. So maybe let's look at some examples here. So if we consider, for example, this vertex here, so the link of this vertex is, well, it consists of 3 vertices, 1, 2, 3. Now these 2 are contained in a common square, so they are linked by 1 simplex. Same for these 2, and same for these 2. So they are pairwise linked. But also, like all the 3 of them together with this one, they are contained in a 3 cube. So we also fill in this simplex here. Here it's similar for this one. I mean, if we look at this vertex here, we again have 3 vertices in our link, and they are pairwise connected. But then after these 3 vertices and this one, they are not contained in a 3 cube, right? So we don't fill in this simplex. And here, well, if we take vertex V here, then our link just consists of 2 disjoint vertices. Good. Okay, and now a simplicial complex is a flag if well, if it is kind of like whenever we have a subset of pairwise adjacent vertices, then they have to span simplex. So we don't want to have holes in some ways. So if every set V1 to Vn of a pairwise adjacent vertices spans a n-1 set. So we see here this one so this link here, so this simplicial complex is flag. I mean, here they are pairwise adjacent the vertices, and they also span 2 simplex. This one is an example that is not flag because, well, again, they are not very stable here. This one is not flag, right? Because they are pairwise connected, but they don't span 2 simplex. So not flag. And here, of course, this again flag because yeah, there are no pairwise connected. That's okay, and now we see the condition for being cat 0 is that it has to be simply connected, and all the links have to be flagged. So if we look at these 3 cube complexes here, okay, now we can look at the thing. So, okay, this one is definitely not cat 0 because it has a link that is not flagged. So it's not cat 0. This one, okay, this link is flagged, and then you can check that all the other ones are also flagged. So this one is cat 0. And this here again is not cat zero because all the links are flag, but it's not simply connected. For all, yes. Yes, for all n, yes. Yes, if every set, yeah, wait. Yeah. Just say if every set of pairwise adjacent vertices spans a simplex, let's say. Better. Thank you. Is there a... Yes, exactly. One can, yes. Exactly, if it's not simply connected, you can take the universal cover. Okay, and well, okay, we see let's have like has this one global condition kind of on this local condition, and we see also that kind of like being not positively, non-positively curved, it makes sense kind of like because here when we have these three squares, that's like a part of a sphere, right? So here we have a positive curvature, so that's exactly what we don't want to have. Okay, now. Some of you probably know that there's a notion for being cat zero for metric spaces. So I will not introduce this because we will not need it, but actually it turns out to be the same. So, so that was first observed by Gromov for finite dimensional cube complexes, and then Leary showed it for arbitrary dimension, also infinite dimensional complexes, is that actually the Euclidean metric on a cat zero cube complex is cat zero. Is cat zero, yeah. Actually, one can say the Euclidean metric on a cube complex is cat zero if and only if the cube complex is cat zero. So if you have a cube complex, like you can equip it with the Euclidean metric. So like you have each cube, you have the Euclidean metric, and you can read through the whole complex. And it turns out that actually the metric notion of being cat zero is the same as this combinatorial definition of being cat zero. Yeah, but we will actually only work with the. So in this course, we actually never work with this Euclidean metric, which is cat zero. We will only work with like the combinatorial structure of the one skeleton. So we'll always consider like the vertices with the combinatorial distance. So if we speak of distance between vertices, we always consider the combinatorial distance. So I mean that's important. Like if you have a square here, right, then the distance between these two vertices is 2 because of 1, 2. It's not a square root. Good. So maybe just a remark on that side. So there may be some ways a more modern way, although that's still disputed, is one could also use the language of median graphs. Okay, there's a definition for median graphs, but actually median graphs are exactly one skeletons of cat-zero cube complexes. So a graph is median. If it is the one skeleton of a cat-zero cube complex, so yeah, so in some ways maybe that's the more reasonable notion, because well, in the end we only work with the combinatorial distance, right? Like we have a graph, we work with the combinatorial distance on the vertices. Why should we introduce this whole kind of additional structure and not just work directly with the graph? So in some ways there are good reasons to rather work with median graphs instead of cat-zero cube complexes. On the other hand, like there's kind of like 10 years or 20 years of literature on cat-zero cube complexes, and then the question is, why should we change the whole notation when there are some historic reasons to do so? So yeah, it's not, I don't know, we will see in 10 years what is standard. For now, since the biggest part of so there are a few papers on this subject written, and most of them we wrote in the language of cat-zero cube complexes, so I decided to stick with this notion, and it's also in some way standard. But also one of the papers that we wrote on this subject is in the language of median graphs. And also if you look in the literature, some books or articles are written in the language of median graphs, other in the language of cat-zero cube complexes, just so that you know it's the same. Yeah, to be a bit flexible. Then yet other results are written like for walled spaces, wallings, and so on, and also it's again it's the same. Yes. Yeah, I can explain you afterwards. Okay, just to not raise confusions. Triangle is not median. Okay, so then maybe let's define orientations. So an orientation on a cat-zero cube complex is just the orientation on the edges. Such that opposite edges in squares have a parallel orientation. So orientation on a cube complex, just like we put on each edge an orientation, but we want that if you have two parallel edges, kind of like they should be the same, oriented in the same direction. Good. So much about the cat-zero cube complex for now, then we will get back later to see more properties of them, but let's first construct the cat-zero cube complex, like the blow-up complex, in which we are interested. So, okay, for this we need the following. Okay, now we go to a group of birational transformations of surfaces. So here we have one important result, this Zariski factorization, that if S and T are regular projective surfaces, and phi from S to T a birational map. Then we can always factorize this birational map in a sequence of blow-ups and blow-downs of closed points. So then we can always write phi as factorize it so into sequence pi of blow-ups, and here another sequence rho of blow-ups. So where pi and rho are sequence blow-ups of closed points. And S and well, that has to be a regular projective. And okay, what we can do is again, so we heard this morning in Michel's talk, like we can also here assume that this set is minimal with this property. So basically one can show that we can choose in a way such that every other variety W where we have such a factorization has to factor through Z. So if we have, okay, let's say we have some set tilde, and here we have a sequence of blow-ups, and here we have a sequence of blow-ups, then this has to factor through Z. So we only blow up as many points as needed and not more. So and choose Z to be minimal, and then the points that are blown up here by pi, these are exactly the indeterminacy points we've seen before, and then the indeterminate points that can be like infinitely many here, but we blow them all up. So are the base points of phi. Of phi, and we denote them by base points of phi. So okay, here one has to be a bit careful. Like I don't want to go too much into detail. Like one has to see where do these base points live, right? Because I mean, here we can blow up points that are contained in S, but then we can also blow up points that are kind of like in the exceptional divisor after we have blown up a point. So for this one has to define the bubble space. We will not do this here. Anyway, what we will be mostly interested is kind of like the number of base points, like how many points do we need to blow up here. Yeah, example which we've also already seen this morning, but let's write it again because it's nice and important, and we will have a look at it again later. We look at the standard quadratic involution, x, y, z to y, z, x, y, x, z, x, y. But we've seen that's not defined at the three coordinate points, so we have to blow these up. We get here this del Pezzo surface of degree 6, and then after we contract this, we have colors here. Perfect. So we have we have these three coordinate lines. So we see them here, and then we contract the coordinate lines and end up again here and have them contracted to points. So here we have 3 base points. And also we are lucky because all of them are already contained in P2, but it could, of course, happen that we have to blow up now points that are contained on this line, so points that we haven't seen down here yet. If the field is perfect, no, I think if it's not perfect, we have to assume regular, because we want that we blow up, it still has to be a regular, I'm not sure. Yeah. Is this clear, or? Let's play it safe. But yes. But I'm not sure if you can do it with. The question is if this resolution cannot happen that we blow up a point and then we have something it's still regular if you blow up a point, but okay, I'm definitely not an expert on these questions. Okay, and in some ways, maybe that's all the algebraic geometry we will need in this course. Okay. We'll encounter some other things, but essentially from this we can construct now the whole blow-up complex. So, okay, we start with S regular projective surface. Then the blow-up complex is the following cube complex. Okay, maybe I can explain just the idea first, the hand waving. So we start with our surface S, and now we blow up points, close points on the surface. And if we take two different points, then we can make precise, like if we blow up one point, we blow up the other point, then we can still consider the other points up here and blow them up again. And then we get isomorphic surfaces upstairs. And so we see this gives some kind of a square, right? We can do this with any number of points. So we get like cubes. And then when we are upstairs on the new surface, I mean, of course, now we have new points that we can blow up, which we could not blow up before. And then this gives us the next. And now we can see how this whole kind of like geography of regular projective models of our surface that we started with are unfolds or so. In some ways, that's what you do. But okay, to do this precisely, we say what the vertices are. So the vertices are these are equivalence classes of marked surfaces. Of pairs. So T phi, where T is a regular projective surface. And phi is a birational map from T to S. Okay, so we say that two of those are equivalent. Well, if they only differ by an isomorphism. So if we make first phi prime and then phi inverse, this gives us a birational map from T prime to T, right? And if this is an isomorphism, then we say that these are the same. Okay. Then we say in next case, what are the edges of this complex? So we say that, so if you have here a class, let's call it T prime, phi prime, and here we have a class T phi, and we connect this by an edge, and also we give this edge directly an orientation. Let's give from this direction, orientation. So if basically these two pairs, they only differ by the blow up in one single closed point. So if again we consider f prime goes with f inverse from T prime to T is the blow up in a closed point. And no, just closed. Yeah. Yes, yes. Yeah, over a perfect field, right? You just blow up a Galois orbit, and then things work as one imagines. But if the field is not perfect anymore, I think. Okay, I'm not working with these things usually. But then all the bad things can happen. Like you can blow up a closed point, and if you go to the algebraic closure, it's not even normal anymore. Like it can really get badly. But okay, and then, then we continue just like that, right? We have squares. It's basically, we start with, basically, like whenever we see a cube, we fill it in. Like if you have, we blow up 2 points here, let's say we blow up the point P, here we blow up the point Q, and then here we blow up both of them, so it commutes, we fill it in as a square, and then also, of course, in general, n cubes. We just continue like that. So, yeah. It may not be an morphism, yes, it's just marking, yeah. Yeah, so n cubes is just kind of like, when we start with a surface, we blow up n closed point on the surface, and then everything commutes, and we fill it in with n cube. Okay, if I don't write down the definition. So we have 2 to the n vertices are contained in an n cube. If there exists one vertex that is represented by a surface, such that we obtain the other vertices by blowing up n of these points on the basic surface. Okay, or should I write it down to be on the same? Maybe let's write it down so that we get the definition correct. So we say V1 to V2 to the n form an n cube. So if there exists a I such that Vi, so let's say this is represented by Si phi I, and we have n points, closed points in Si, and all the VH, so for all j equal from 1 to 2 to the n, we have that Vj is given such that Vj, so Vi inverse composed with Vj, so from Sj to Si, is the blow up in some of the points Pi. Okay, let's maybe, before I erase this one, let's just make a picture. So how does it look, for example, like if we take this resolution here of this sigma? So if we start here with, so we start with P2 identity, right? And now we can blow up these 3 points, right? And then we can blow them up again. So we get this 3 cube. And then up here we are at this surface, let's call it S. So it's the Petzov degree 6, and here we have pi, right, that goes down here. And now what we can do here, we can again, now we can, once we are up there, we can contract the 3 green curves, which we could not contract before, right? So we can contract one of them, the other one, and the third. And then here we end up again on P2, but this time with the marking sigma, because to get back from here, well, okay, sigma is an involution, so it works well. We have to blow up again these 3 curves that we contracted, and then contract these 3, and then we are here. Yeah, and then of course here we see there's more cubes like here. Like once we have blown up these 2 points, then we can already contract one of the lines. It's disjoint, and then it commutes with this one, or also here. So it looks like that when you just consider the 3 like this. So that's a part of our cube complex. Now, of course, our observation is like this cube complex is not at all finite dimensional, because there are infinitely many closed points on our surface. So we can have cubes of arbitrarily high dimension. It's infinite dimensional. So there is, okay, it's infinite dimensional, but it's even like, it's also not locally finite and not locally finite dimensional. So at each vertex we can have, at each vertex we have cubes. So each vertex is contained in cubes of arbitrarily high dimension. So yes, so in some ways, right, if you have well, not the cube complex is always very large, but if you have a given thing and then you can look always like to get from one to the other, like can you do it by passing only through cubes of bounded dimension, then we could tell something about that. So yeah, so maybe let's just observe, like, okay, the easiest observation is that actually it is connected. And this we just use the Zariski theorem. So, I mean, if we have here, two marked surfaces, T prime, phi prime, and T phi, right? And then, okay, we can look at the factorization from T prime. So here we have rho, here we have pi, here we have rho z. So here we have a phi inverse composed with phi prime. Okay, then what we can do here, we can just consider up here the marked surface Z with the marking phi prime composed with pi. Right, so we first go down to T prime and then to S. And this one is connected here by a sequence of blow-ups, which correspond to edges in our cube complex. But here we see with, because we have this factorization, we see that this is actually the same as that phi composed with rho. And then here we have then again path that goes down here to phi. So basically Zariski theorem gives us that the cube complex is connected. But what we have more is that actually it is simply connected. And the proof is, well, explain, okay, I have 5 minutes. Yeah, that should be enough to show it's cat 0. So if gamma is a loop in our cube complex, of course we can deform it by homotopy so that it's contained in the one skeleton. And okay, so it's a loop in the one skeleton, so it passes through finitely many vertices. So let's call them S1 phi 1 up to Sn phi n. Okay, and now again, kind of like just applying Zariski like for multiple things. We find one vertex that dominates all of them. So basically, we have here, we have here our path, our loop, right? And here we have all our si's, phi i's. And now we find here a vertex W psi, such that we reach this one here all through blow-ups. Small exercise to see that such a vertex exists. And okay, now what we do is we want to, or the basic is we want to just shrink this loop up to this vertex that dominates all of them. And the way we do this is, well, first of all, we remove the backtracking. Right, if the loop makes here and then it goes back on the same edge, we can just pull it in. And then the next part is basically, well, we can just choose one. Okay, I have to. So we choose one. So if you have one Si by I, now if we go from here to the next vertex, either kind of like it's a blow up or a blow down. So either the Picard rank goes up or it goes down by 1. So what we do is we just take one where the Picard rank is minimal. So there we know that basically in both directions it's given by a blow up. So blow up, and it has to be blow ups by 2 different points. So this means we can just complete this to a square. And now we kind of homotope the loop from here up to here. And this one is still dominated by this one. And now we either reduced the minimal Picard rank or we reduced the amount of vertices with minimal Picard rank. So if we continue this recipe, at some point our loop will be here homotoped to a point. Yeah, so that's the proof. And yeah, let's just quickly idea to say that also actually all the links are flag. If you have a vertex of the blow-up complex, then the link of V is flag. Well, let me also here just explain it by hand. So, okay, we have here a vertex, and now, okay, we have the ones that are centered, just given by blowing up. And now, what we want to show is if we have a simplex set of vertices in our link that is pairwise connected. So we have all our we have a set of vertices in our link that are pairwise connected. So these correspond to here these adjacent vertices in the cube complex. And okay, some of them are kind of like ascending, the other ones are descending, they are given by contracting curves. But now we know that they are pairwise contained in a square. So this means here we can complete to a square. Okay, this means that the points where it corresponds to blowing them up, they have to be, well, 2 different points. And then the ones where we go down, where we contract them, if you want it to be if it should commute, so we can contract this one, and then it has to be in a square. This means that the corresponding curves have to be disjoint. And also these points cannot lie on the curves, because again, otherwise it would not commute. So in this thing, means we can just contract all these curves. We end up on a surface S where we have our n different points, and hence this implies that this whole these n vertices are contained in a simplex. Okay, so so I just leave it here orally. But it's good to think about it for a moment yourself. And but okay, so with these 2 lemmas, we see that our blow-up complex is indeed cat0. So we have a nice cat0 cube complex. And yeah, we will continue tomorrow here. We will see how BRS acts on this cube complex, and then we will see what properties cat0 cube complexes have that we can use in order to say something about our group BRS. Thanks a lot.
You pick the minimal Picard rank, and then you have 2 edges. I mean here.
Here, so you have 2 edges that depart, yes.
And then you blow them up, so you got the vertex above.
Yes.
Why this vertex is also below the vertex of the square?
Just because we blow up. I say the vertex W we get by basically blowing up all these points. So basically, yeah, it's just basically blowing up. This one is under it, blowing up. This one is under it, it's also blowing up. Also.
So given a median graph, if it's a unique way to extend it to cat-0 cube complex.
Yes, yes. So basically, you just take the so-called cube completion. So you look at the graph, and whenever you see a cube, you fill it in with a cube. So basically, whenever you see like have the one skeleton of a Euclidean cube, you fill it in with a cube.
Okay, so the way of completion is given.
Yes.
Is it correct? Am I drawing the correct conclusion that cat-0 cube complex is contractible?
Yes. Circle components are contractible. Yes. Yes.